In this problem, we're given a hip stem made of titanium alloy. And this titanium alloy has a yield strength of 115 ksi, both in the tensile and the compressive direction, and also has an elongation of 10%. We're going to treat the hip stem as a simple cantilever beam, as shown here, where we have a force applied of 200 pounds in the negative y direction, and then a torque of 110 pound-inches applied at the end. And we're asked to calculate the factor of safety using the appropriate failure theory. And we're going to look at a conservative and a non-conservative failure theory. Once we have our stress pair for our principal stresses, we'll plot that on a plane stress diagram and compare that to the failure theory boundaries. So the first question, when we are trying to figure out what failure theory to use, is what is our elongation of failure? In this case, our elongation of failure is greater than 5%, so therefore we should be using a ductile theory. And the second question, when we go the ductile theory route as well, do we have a different compressive yield stress? And in this case, we don't. The yield stress is the same in compression as it is in tension. So that leads to two theories: the distortion energy and max shear stress. So the max shear stress being the more conservative of the two. So the next thing we need to do is figure out what our stresses are. So we have this force out here that's applied. So our moment is going to simply be the force times the distance. And in this case, we'll use this length L, because we're going to look at the max stress here as the bending stress gets higher as the length from the applied load gets higher. And so this is 200 times 4, which equals 800 pound-inches. For our torsional stress, it's the same throughout the length, and it is going to be dependent on this torque value of 100 pound-inches. So our torque is equal to 100 pound-inches. So we can calculate our bending stress. We're going to designate this as the x direction and this is the y direction, is mc over I. Found our moment. C is going to be related to our diameter. This is a round cross section, so C is our diameter divided by 2. And then I is pi d to the 4th divided by 64. And d is again 0.42. So this gives us a stress of, well, no, we're going to call it 110.0. KSI. Torsional stress is going to be TR over J. with T being our torque, 100 pound-inches. R is our radius, so again 0.42 divided by 2. And then J, which is pi, diameter of the fourth, divided by 32. This is for a circular cross-section. And we get 6.87 KSI. So those are the two stresses that we have at this element on the top of the beam here. The bottom of the beam, the sigma x would be exactly the same, except it would be compressive, and the shear stress would be the same. So we need to find our principal stresses, which are given by the following equation. So in this case, our sigma y stress is 0 because there's no stress in the y direction on the top of the beam. And so then we get, putting in the numbers, divided by 2. And we get 110 divided by 2 plus or minus 110 again divided by 2 squared this time. Okay, so this gives us our principal stresses. So 110.42 and negative 0.428 KSI. So now that we have these two principal stresses, we need to reorder them such that sigma 1 is greater than sigma 2 is greater than sigma 3. So we put the 110 as sigma 1, sigma 2 is 0, and then sigma 3 is negative 0.428 KSI. And we need to reorder those so that all our equations for our failure theories work. We'll start with the most conservative, which is the max shear stress. It's conservative. So our max shear stress is equal to sigma 1 minus sigma 3 divided by 2. And the failure theory is that it must be greater than the yield strength that's done in tension divided by 2. So in order to calculate the factor of safety, we have the ratio of that yield strength to sigma 1 minus sigma 2, the two principal stresses. And we get 115 because we know this from the problem statement as the yield strength divided by our two principal stresses. And this gives us a factor of safety 1.037. That's our first factor of safety. Now if we want to do our less conservative or non-conservative distortion energy, we have the von Mises stress, which is the square root of basically the difference of each stress component squared. Divided by 2. We have 110 squared plus 0.428, minus sign there, and there we go, square it, square root, and that gives us 110.63 KSI. So then our factor of safety for the factor of safety for our distortion energy is sigma y, our yield strength, divided by our von Mises stress, which is 115 KSI that we were given, divided by our 110.63 KSI. And this gives us 1.39. So just a slightly higher factor of safety than the 1.37 value that we got with the max shear stress. So these are in a location where the curves are not very different at all. So let's go look at the plane stress diagram where we have our two principal stresses, sigma 1 and sigma 2, and the two different failure envelopes. So the ellipse gives us the von Mises or distortion energy theory, and then the polygon gives us the maximum shear stress theory. And here sigma 1 is labeled. We're actually going to put sigma 3 here and sigma 1 here. Alright, so our yield stress, which is right here, was 115. So each one of these graduations is 20. And so we had a stress of 110. So we're roughly here, and then we had a very, very small stress. So our point is right below the x-axis right here, and you can see at that point there's very little difference, if any, between the von Mises and the maximum shear stress theory. So this is 110 minus 0.428. That's the location. If we had a point down here, you would see a much bigger difference in the factor of safety.